Good morning, ladies and gentlemen, and thank you for logging into our webinar on the business case for CHP in process and manufacturing industries. My name is Keith Stocker and I'm Market Sector Manager for Gas Power Solutions for Finning UK and Ireland, and I'm here with my colleague Nigel Thompson, Sales Manager for Gas Power Solutions at Finning UK. We are also privileged to have with us Jonathan Graham, a Policy Manager at the Combined Heat and Power Association. Questions can be placed on the Q&A board on the website during the webinar, but we will save the Q&A session for the end. Our aim today is to introduce you to the topic of combined heat and power and discuss what is CHP, why CHP can be of benefit to the process and manufacturing industries, Finning Caterpillar experience with CHP in the UK and the technologies and services we can offer, and evaluating CHP for a specific site application. Jonathan will then go through some of the legislation and incentives that are in place for operators of good quality CHP systems. I will now hand over to Nigel for an introduction to CHP.
Hello everyone, thank you Keith. Starting with the concept of what is CHP, on screen you'll see a general definition of what combined heat and power entails, or is. In comparison to traditional methods of providing heat and power to a building, or process, or site, the CHP will utilise more of the energy contained within the fuel. By doing this, less carbon dioxide is released to the atmosphere, which is a benefit Jonathan will describe in further detail later. There are some words and phrases floating around to the right of the screen indicating the terms associated with a modern CHP system. This schematic illustration, now displayed, shows the main elements or items of equipment and plant that are usually installed in the systems we are considering today. The arrow pointer will move around the slides to indicate the various elements that I am describing. We start with an internal combustion engine, spark ignition, or commonly abbreviated to SI. A compression ignition or diesel engine can be used, but the economics do not normally favour a liquid-fueled engine. An alternator coupled to the engine, producing power at 400 volts, 3.3 or 11 kV or other voltages as required by the site. A separate circuit aftercooler or secondary cooler, or also known as an intercooler circuit, comprising a pump, a three-way valve and the intercooler itself, which is a heat exchanger in which the gas and air mixture, which has been compressed and so heated by the turbocharger, is cooled before it enters the engine. The intercooler is cooled by a water-based circuit at around 40 to 45 degrees C, which is normally too low a temperature to recover. So this heat is rejected or dumped by a dry air cooler, which is essentially a horizontal radiator drawing air from the ambient conditions via the fans and dissipating the heat to atmosphere. The jacket water circuit, comprising a water pump, oil cooler, which is a shell and tube oil cooler usually fixed to the engine and comprising part of the engine. The engine water jacket circulating around cylinder liners and cylinder heads, and also a three-way valve to ensure optimum operating temperature. The coolant in this circuit recovers heat from the engine and also traditionally from a shell and tube heat exchanger placed in the exhaust gas stream. The gas going through the tubes, the water flowing around the outside of them. Typically, the heat is then passed to the process or heating system at a plate heat exchanger, which is normally made of stainless steel. The client system can typically be heated from an inlet of say 65 or 70 to an outlet of 85 or 90 degrees C. After being cooled, this primary circuit returns to the engine inlet. In the event not all the heat is used by the process or site, some or all of the recovered heat can also be dissipated or dumped by diverting the return leg to a separate circuit of the dry air cooler. This is also dissipated to atmosphere. Why might CHP be suitable for a particular site or building or process or application? There are financial benefits, which include tax incentives such as enhanced capital allowances and business rate exemption. Jonathan will expand on these later. DEC also has some useful information on their website. A low cost of ownership compared to other plant, and typically the CHP provider will support their product with an all-inclusive operation and maintenance service that takes the risk away from the equipment owner or host. What other business drivers are there to make the case for investing in a CHP? An embedded generator enables the owner to import less power from the grid or utility provider, the DNO, thus reducing impact of triads, the three most expensive half hours of power in any given year. A combined heat and power unit can also stabilise a supply that may be at or near capacity and is a proven, reliable, low-risk solution. In many cases, a lower cost than having a second incomer provided to the site, or for instance having an HV line extended. The cogeneration system will also be designed with the site's specific needs in mind. The CHP also provides environmental benefits when compared to the traditional method of providing power to a process or site from the grid or utility and heat from gas or liquid-fired boilers. There is a carbon dioxide emissions reduction and an attached value to this, and again Jonathan will outline more on this later. That represents a financial incentive in addition to being a tool to help the company achieve stated goals, such as being green. Keith will now present in a little more detail some of the more frequent configurations of CHP systems.
Thanks, Nigel. With a standard power-only generation system, all the heat generated by the engine cooling system and potential heat from the exhaust is rejected to the atmosphere. This can mean as little as 40 to 42% of the energy input to the system is being utilised. Whilst the CHP system is set up to recover heat from the engine cooling circuit and exhaust gases, it can be configured to reject this heat and still allow the unit to run at full output. This may be required for a blackout scenario when the CHP is running as a standby generator, or could be a commercial decision based on the comparative value of electricity and gas. This comparative value is known as the spark spread. The return flow is diverted to the heat rejection radiator or dry air cooler via a 3-port valve where the heat is rejected to atmosphere and the return flow cooled to the required temperature of the engine cooling system. The diagram shows the exhaust heat included in this primary circuit. With some systems, the exhaust gases can bypass the exhaust gas heat exchanger here, and the exhaust gases are put directly to atmosphere at their high temperature. This allows for a smaller radiator to be used as less heat is rejected through this primary circuit. The ideal scenario is always to be utilising the maximum possible amount of heat and power generated by the CHP, and this is by recovering all the heat as low temperature hot water from both the engine water jacket and the exhaust. The diagram on screen shows this scenario based on a single stage aftercooler system where only the engine water jacket and oil cooler heat is recovered. Sorry, excuse me, it's recovered, with the low grade heat from the aftercooler being rejected. In most modern gas engines there is a 2-stage aftercooler, with the first stage being high temperature and circuited in with the engine water jacket circuit. In these cases, up to 88% of the energy being put into the system can be recovered as power and LTHW. This can further be enhanced if a use can be found for the lower grade stage 2 aftercooler heat. Heat recovery from CHP is not an either-or situation. If there is a fluctuation in the site heat requirement and it can no longer utilise all the heat produced from the CHP, the control system will detect a rise in return temperature and start to divert some of the return flow to the radiator via the 3-port valve, where an element of the heat will be rejected to atmosphere. If the return temperature continues to rise, the system will increase the flow to the radiator until either the return temperature stabilises or all the heat is being rejected. Should the owner decide for financial or ecological reasons not to want to reject heat, an alternate control algorithm can be used. In this scenario, as the return temperature increases, the control system will downrate the output of the engine until either the return temperature stabilises or the engine reaches around 50% output, at which point it will undergo a controlled shutdown and wait for the return temperature to drop to the design condition. Whilst this system reduces the power and heat output of the CHP, it also reduces the amount of fuel required and thus maximises the system efficiency. Previous slides have concentrated on producing LTHW from all aspects of the generator system. However, it is possible to generate different types of heat from different sections of the system. For example, a waste heat boiler can be installed in the exhaust flue to generate steam, should there be such a demand on site. This slide shows a standard waste heat boiler setup. However, this can be built into a combination boiler that also incorporates a gas or dual fuel fired section, allowing steam production from the boiler when the CHP engine is offline. Medium temperature hot water can also be generated from the exhaust flue system in a similar way. LTHW can still be recovered from the engine water jacket, and the system efficiency can be further enhanced by fitting an economizer downstream of the boiler to pick up any residual heat in the exhaust gases as LTHW. For many sites, the use of all CHP heat can be a problem, especially in the summer months. However, if there is a chilled water requirement, the surplus heat can be used in an absorption chiller to produce chilled water. Absorption chillers use the low temperatures required to evaporate water under a vacuum to further chill already low temperature water, standard operating conditions being around 12 C return and 6 C flow temperatures. The water within the chiller is transported around a closed loop via a chemical, usually lithium bromide, and the heat from the CHP is used to separate the water from lithium bromide in the generation section of the chiller. The attached slide shows an LTHW fired absorption chiller utilising the site LTHW distribution system. This setup allows the CHP heat output to be easily utilised as both heat and cooling depending on the site requirements. More modern double effect chillers can use the engine exhaust gases directly into the chiller with a boost provided by the LTHW from the engine water jacket. This setup generally enhances the coefficient of performance of the chiller and hence the overall efficiency of the system. Nigel will now look at the fuel sources we can utilise.
To power a CHP engine. The vast majority in the UK burn gas. Natural gas is the most common fuel source, and while still a fossil fuel, is clean, especially compared to coal or diesel in terms of emissions, and remains a relatively low cost. The majority of fuels in the UK can be utilised to power a CHP engine. The vast majority burn gas. Natural gas is the most common fuel source, and while still a fossil fuel, is clean, especially compared to coal or diesel, and remains relatively low cost. Biogas is a generic term used to describe all gases produced as a result of a biological process, and thus includes landfill gas. We have extensive experience in the operation of biogas generation, including in the sewage industry, which produces gas by anaerobic digestion, known as AD. Typically, this gas has 55 to 60% methane content. Food and agricultural AD plant The latter, as covered on Country File recently, numbers are increasing significantly year on year. This image indicates the possible interconnections physically and in terms of possible energy provision of a site or building. For example, we have a commercial facility and/or an industrial facility or a manufacturing plant receiving its power from the grid and raising heat for its processes and personnel heating via conventional boilers. There may be a standby diesel genset on site acting as a standby to the grid to provide power to the facility in the event of a mains failure. This could be to save a batch of product that would be rendered waste if power were lost, so this genset ensures the site remains active. It is possible to integrate a CHP into this existing infrastructure, powered in this example by natural gas, to supplement the heat and power requirements. All of this can be seamlessly integrated and effected to ensure optimum operation for the client site. I will now hand you back to Keith, who will give you some further insight into Finning UK.
Thanks, Nigel. Finning UK is part of Finning International, the largest and one of the oldest Caterpillar dealers in the world, covering Western Canada, 4 countries in South America, the UK and Ireland. And we recently celebrated 80 years of being a Caterpillar global partner. Finning Power Systems has over 25 years experience in the UK in on-site power generation, including mission-critical standby systems in hospitals and data centres, standard non-essential standby, and a variety of gas-powered systems including landfill power generation, biogas CHP for anaerobic digestion, sewage treatment works, and naturally gas-fired CHP. We are also working on a number of syngas projects, and our first is currently at the commissioning stage. Finning currently offer a wide range of Caterpillar high-efficiency, low-emission generator sets, starting at 400 kilowatt and peaking at 4.3 megawatt for single engine, with many of the power nodes also being available in biogas applications. We offer full turnkey packages covering all aspects of generation, heat recovery, sound attenuation, and mechanical, electrical, and civil integration works into the site, and regularly undertake the role of principal contractor under CDM regulations. We can undertake or assist in all planning and permitting requirements, including connection applications and G59 testing and approval. We have over 30 field-based gas engine specialist service engineers across the UK and Ireland, backed up by 23 branches, the Caterpillar logistics system, which allows for next day delivery of over 98% of the parts required, and a remote monitoring desk at our Slough branch, which is manned 24 hours a day, 7 days a week by control technicians. This allows us to offer all-inclusive maintenance and repair contracts with high availability guarantees to maximise the customer savings from the system. It is important to be careful in selecting the supplier of a CHP system. Looking for the dealer of the generator set selected is a good option, and it is preferable that the supplier is capable of providing full in-country after-sales service to ensure a long-term, efficient and viable solution. Finning Caterpillar over 400 megawatt of on-site gas power generation operating in the UK and Ireland on landfill gas, biogas and natural gas CHP, with over 100 sets being monitored from the control desk at Slough. CHP applications include hospitals, urban district heating schemes, pharmaceuticals, manufacturing sites, universities and sewage treatment works. And as I said, we've also now started looking at our first syngas project as well. So how to analyse the feasibility of the site for CHP? Back to Nigel.
Thanks, Keith. We'll now run through an indicative review of how to consider or what steps need to be undertaken to establish whether a CHP project is viable for a site. Simplistically, this slide depicts the black box tasks in order from the commencement of an energy audit to the decision to implement a purchase. Let us consider the fuel. You probably have a natural gas line into the site. Can the provider give you a consistent pressure? Is your supply deemed interruptible? Can they provide the new volume requirement? It is worth noting that installing a CHP unit actually increases the amount of gas consumed. Are there, or could there be, renewable fuels available? Establish what the site demands are for heat, power, steam, and/or cooling, and, more importantly, what they will be in a 5 to 10 year forecast of energy use. Are there energy saving measures already underway that will reduce the site energy demand? Know what your current utility costs are, and again, try to obtain an idea of what these would be if you implemented a CHP on your site. Some DNOs may raise the tariff if you significantly reduce your imported power. Is your demand constant or cyclical? What are the minimum and maximum values? Traditionally, the best return on investment is achieved when the CHP is sized to provide slightly more than the base load power requirement. But if in doubt, an undersized CHP will still save money, whereas an oversized unit will not. Could a CHP unit physically fit inside the boiler house or energy centre, or will it need to be placed outside in a container? Having conducted a feasibility analysis, we essentially arrive at a go, no-go gate. If a CHP doesn't appear to be viable in the short term, revisit the concept in 3 to 4 years' time to reevaluate. Energy usage or technology may have changed in that time. Having gone through the feasibility process, and with indications being favourable for the installation of a CHP unit, the technical factors need to be considered. Would it be inside or outside? Are there any stringent noise limits to hear? Are there any neighbours who may object to any new noise? What is the optimum heat or power rating? Is it 800 kilowatts electrical? Is it 2 megawatts electrical? Is it 1600 kilowatts thermal? Will the unit be heat or power led, i.e. which product is the most valuable to the site and will determine how the CHP is configured in its controls? Consider what the operating regime of the site is. Is it 24 hours a day, 7 days a week, 50 weeks a year? Or 24 hours a day, 5 days a week, 50 weeks, or any combination? This will determine the predicted annual operating hours per annum and therefore the O&M price. Most manufacturers or suppliers of CHP will provide a fixed rate O&M, whereby, for instance, around 1 pence per kilowatt hour of electricity produced, they will supply all parts and labour for routine servicing, as well as covering any unscheduled downtime and including overhauls, typically for periods ranging from 5 to 15 years. These will establish a baseline and increase via a RPI mechanism or similar. Lastly, purchasing a CHP unit is not the same as, for example, a standby diesel genset. The lowest initial cost is not the best measure in order to achieve the savings or payback potential. The CHP must firstly run, which means it must be reliable, durable, and for excellent results have good electrical efficiency. For example, the CG range of Caterpillar CHPs we spoke around earlier were in the 42 to 43% electrical efficiency area, which means a conversion of the energy content in the gas into power produced. There has to be a trusting partnership relationship rather than a purchaser-supplier relationship. After all, the two companies could need to work together effectively for a long time. The ability of the CHP provider to support their product is absolutely key. A fantastic O&M rate or deal on paper becomes worthless if the maintainer ceases trading or breaches a contract for continual underperformance. I'm pleased to now hand over to Jonathan Graham of the Combined Heat and Power Association, who will outline some of the relevant incentives and legislation relating to CHP units.
Thank you very much, Nigel. My name's Jonathan Graham. I'm the Policy Manager at the CHPA, or the Combined Heat and Power Association. The CHPA is devoted to creating a more local, efficient, and less costly energy system, one that is in greater control by the consumer. We have about 97 members, and this includes both users of CHP as well as providers and suppliers of CHP and other energy efficiency technologies. So we are focused on CHP, but also on energy services such as energy management and district heating and cooling services. I wanted to just give a brief overview of CHP in the UK. There are more than 1,900 sites, CHP sites in the UK, and many of these are very small scale, often less than 2 megawatts. CHP growth in the UK is very steady. Last year saw at least £200 million of new investment in gas-fired CHP. And CHP now makes up about 6.5% of the UK electricity generation system. CHP is used in a number of businesses and industrial processes, and that is why it's many well-known brand names, well-known companies across the UK use CHP to provide their heat and power, including brands such as Boots Company, British Sugar, Diageo, Weetabix, Jaguar Land Rover, Tesco's, and many others. Especially fast-growing section of the CHP industry is the smaller than 2 megawatt sector, which, based on survey data performed by the CHPA of its members, has shown steady growth over the last few years, with hundreds of sales each and every year. We are expecting that strong spark spreads, especially for on-site power generation, and an increasing desire for businesses and industry to have control of their own power supply will continue this growth in coming years. Looking now onto some of the areas of policy, there is an increasing focus in policy on away from renewables and onto cost-effective carbon reductions and energy efficiency. Okay, sorry about that. That was just a bit of a technical snafu, but looks like we're all back online. We are I was talking about sort of the policy environment for CHP, and there's an increasing shift away from renewables from policymakers and onto more cost-effective carbon reductions, such as energy efficiency. This is happening at both the EU level, where policy such as the Energy Efficiency Directive is delivering, is focused on improving energy efficiency investments across European member states, and is also seen at the EU level when they're looking at their carbon commitments for 2030. This is coming down and is also occurring at the UK government level, where there's an increasing focus on CHP and other efficiency investments, and as a way to decarbonize heat, especially industrial heat. We're also seeing it happening at the political level, where all major political parties support CHP and recognize the value that CHP can provide to both the UK economy and the UK environment. Between the EU and UK and political direction of travel, we are starting to see an increasing political and policy focus on energy efficiency generally and on delivering new CHP capacity specifically. Going now to look at a few of the key incentives and policies which affect CHP. These are the major carbon taxation policies that impact those industries that generate their own heat and power through technology such as CHP. The climate change levy, which is a tax on gas and electricity for non-domestic users. The carbon price floor, which is a tax on fuel used for electricity generation and meant to balance, to strengthen the EU emissions trading price. The carbon reduction commitment, which is a tax on all organizations using more than 6,000 megawatt hours of electricity per year. And the EU emissions trading scheme, which is a European-wide cap and trade scheme, which allows companies to trade allowances as needed. On many of these taxes, there are currently incentives for those who operate and use gas CHP. The fuel used, CCL relief for all fuel used in CHP Sorry, another technical snafu. For CHP electricity generation, it receives a relief from the climate change levy for all electricity supplies which are used on site, which is also known as direct electricity supplies. This has a value of over £5 per megawatt hour. CHP operators can also receive enhanced capital allowances, which is the ability to write off 100% of equipment costs against taxable profits in the year the equipment is purchased, providing a significant incentive. We also have a new incentive for CHP, which has just arrived in April of the last year, announced in Budget 2014. As part of that budget, the Chancellor announced that all CHP electricity generated and used on site will be exempted from the carbon price floor starting from April 2015. For CHP generating 6,500 megawatt hours annually, this provides a value of at least £26,000 each and every year. Or you can also think of it as a value of about £4.20 per megawatt hour generated and used on site. Looking beyond specific incentives, the fact is that carbon prices are rising at a very steady pace. This includes both the EU emissions trading scheme as well as the carbon price floor. As these costs rise, the ability to mitigate these costs, but through lower carbon emissions on site, are very valuable. And we are seeing that CHP can help to do so. There are a number of other areas of policy which can be helpful. We don't consider them incentives because they simply lower the playing field, level the playing field for CHP and other generators. This includes a relief on all fuel used for heat generation, and the reason for this is that because boilers are not required to pay carbon price floor, the government has agreed that half the fuel, or a little more than half of the fuel used in CHP, should not be applied. The carbon price floor should not apply to them. Business rates exemption, which applies to other power generating plants and therefore also applies for CHP. Free allowances in the EU emissions trading scheme, which recognizes that a number of installations do not have to pay EU emissions trading scheme, whilst CHP does. And the embedded benefit, which recognizes that CHP generated electricity does not use the transmission system and therefore should have to not pay for its costs. I briefly mentioned the carbon reduction commitment, and this impacts CHP. New Phase 2 rules, which started in April 2013, are more favorable to CHP than previous Phase 1 rules. CRC participants must now report and pay for supply of electricity they receive from CHP, but the gas supplied to CHP installations is exempt from CRC. I've talked a little bit about the incentives and the opportunities for incentives for CHP operators. It's important that CHP operators achieve what's called good quality CHP. The reason for this is that European regulations and law do not allow CHP operators to receive incentives for their output unless they achieve good quality status. The good quality status is determined by a scheme called the CHP Quality Assurance Scheme. This determines the overall efficiency of an individual CHP scheme. The CHPQA uses a quality index score to determine the CHP's efficiency and fuel savings compared to if if both the electrical efficiency above 20% and the QI exceeds 100, it's considered good quality status, and it can achieve many of the incentives which I referenced earlier, such as on climate change levy and carbon price floor. If those numbers do fall, and the QI, for example, falls below 100, then those incentives are scaled back. There are opportunities for CHP generators from generating power on site, especially as we start to reach a period over the next few years where the electricity market capacity is falling and there's increasing pressures to find necessary electricity for the grid. CHP generators can take advantage of this in providing balancing and grid services, capacity services, such as capacity market, the demand-side balancing reserve, the short-term operating reserve, and through Triad. The specific values of these services will vary greatly from year to year and often depend on bilateral agreements. But the ability for a CHP generator to provide power when the electricity network needs it can become quite an opportunity. I've talked a lot about fossil fuel CHP, especially gas CHP, but I also wanted to talk briefly about biogas CHP, which is a form of renewable energy, and because of that, biogas CHP is able to collect support for both its renewable electricity and its renewable heat. Renewable electricity receives support from either the Renewables Obligation or the small-scale feed-in tariff. The small-scale feed-in tariff is a flat payment for the renewable electricity generated over 20 years, and the Renewables Obligation is a tradable certificate provided for renewable electricity, also for 20 years. Renewable heat is supported through the Renewable Heat Incentive, and a generator is able to receive both the support for its electricity through the RO or the small-scale FIT, or can receive and also simultaneously receive support for its heat through the RHI. I'm going to talk a little bit more about the Renewables Obligation. Generators receive the Renewables Obligation certificates, which have a value of approximately £40 per megawatt hour, although they vary from year to year. And an anaerobic digester will receive 2 ROCs per megawatt hour until April 2015. Support will reduce in 2016 from 1.9 ROCs and then 1.8 ROCs. Although those ROCs, the amount of renewables obligation certificates you receive will remain steady over the 20-year lifetime of the plant. The scheme for Renewables Obligation will end in 2017, although there will be an opportunity for a different scheme that is just launching later this year called a Contracts for Difference. Small-scale feed-in tariff scheme is designed for smaller size generators. Facilities of less than or equal to 250 kilowatts are entitled to 12 pence per kilowatt hour. Facilities that go up to 500 kilowatts are entitled up to around 11.5 pence per kilowatt hour. And facilities between 500 kilowatt and 5 megawatt are entitled just under 9.5 pence per kilowatt hour. If you're able to export power, there's an additional rate of 4.7 pence per kilowatt hour in addition to the market rate. As I said, you can achieve both support for your electricity as well as your heat as a renewable generator, as a renewable CHP generator. And this means you can also access, as a biogas CHP, support for your heat. That's currently up to 600 kilowatts. You can receive a little under 6 pence per kilowatt hour, and then as you go over 600 kilowatts, you can receive over 2 pence per kilowatt hour. As with the support under the Renewables Obligation and feed-in tariff, this support lasts for a number of years. In the case of the RHI, it is a 20-year support mechanism, and it stays steady for those 20 years.
Thank you very much, Jonathan, for joining us today and providing the overview on what running a CHP plant entails. In summary, we hope that all our audience today have found the webinar informative and relevant to their situation. The content has also, we hope, provoked some thoughts for you on the various drivers that make installing a CHP unit a sensible, viable option. A variety of considerations are indicated on the slide now, but there may be others unique to your situation. We would be happy to provide assistance or advice on any of these for you. We will now proceed to answering the questions posed during the course of the presentations, which Keith will chair. If we do not have time to address them all, please be assured that your question has been logged and we will follow up with a response to you outside of the webinar. Thank you for your interest.
Thanks, Nigel. Thanks for your questions we've had in so far. Jacob, yes, we followed and we can see where your confusion comes from. The flow of the arrows is not incorrect, but I can see where the confusion comes, and yeah, we will slightly tweak that diagram for our next webinar just so that it's a bit clearer. But yeah, I can see where the confusion comes from about the way the arrows are showing the flow around the circuit there. For your second question with regards to syngas, yes, it is. We do have to derate the engine running on syngas. Syngases generally have a very low amount of energy in the fuel, and that has a big effect on the performance of an engine. Every syngas project that we do, we look at individually. We ask for a gas analysis of what is expected to come out of the gasification system. We work very closely with our colleagues at Caterpillar to then model the effect of that on the performance of the engine and produce a data sheet to show how we think a certain model may operate depending on the type of gas that we're putting in. And to give you an example, we're using what would be considered a 1950 megawatt biogas engine at the moment, but with the syngas project that we're looking at, we're expecting it to be running at about 12 to 1400 kilowatts, just to give you an idea. Judith, thank you for your comment. Yes, I imagine it is possible to recover additional heat from the exhaust gases of an oil boiler. You could put an economizer in similar to what we would do with the steam boiler on a CHP system. It's not something we would look at specifically because it's not what we would define as combined heat and power. We're not generating power out of that system. But yes, I don't think that I imagine yes, you could take additional heat from the flue gases of an oil boiler if you wanted to. So thank you for your question. I have a further question from Elizabeth. What is the typical payback period? I'll let Nigel have answer that one.
Okay, thank you. In terms of a payback period, a general period to quote would be between 3 and 4 years for the payback of the installation costs. but this depends very much on the spark spread and the annual operating hours configurable to the site. So it does vary from site to site, even from site to site within the same industry. Just touching actually on the syngas question we had, in terms of energy content in the gas, a syngas may have between 5 and 8 megajoules per meter cubed, compared to a natural gas of 34 or 35, or a typical biogas from an AD plant may have around 19 megajoules per meter cubed. So in terms of energy content, we're looking at perhaps a third of a typical biogas content. I'll take the question we've had on the typical cost saving in energy costs. It's hard to quantify what the cost saving will be, because again that depends on the site cost at the outset, what their utility costs are for the gas, what their heating costs are, and what their power requirements are. So a typical cost saving could be minimum of 15%, but it's hard to give a general figure for every site.
Carbon price support. If I could ask Jonathan to answer that.
Thanks, Sheriff. So the question is, what is the approach for carbon price support exemption on electricity used on-site from April 2015? It's a good question. The government announced in April this year that there would be this on-site exemption from carbon price floor in April 2015, but the specifics have not yet been announced. Right now, the CHP industry, led by the CHPA, is in discussions with HM Treasury on the specifics of the regulations. We're expecting a decision in the autumn of this year for the regulations to then be put into through Parliament in the spring of 2015. Based on initial discussions with Treasury, we think the aim will be to keep the exemption in line with the on-site exemption under climate change levy, but the devil will very much be in the details.
Okay, thanks, Jonathan. We've also got a question from Sean regarding the performance between natural gas and biogas, so I'll let Nigel answer that one.
Thanks for the question, Sean. If what I'm about to say doesn't answer your question, if you submit it again, we'll take another look. But in terms of energy performance, natural gas versus biogas, the efficiency of the engine is usually very similar, depending on the fuel. With a lower energy content in the biogas, you'll have more volumetric flow. Your heat recovery side is also very equivalent in terms of the kilowatts you produce and the temperatures at which you produce it. So whichever fuel you have, you can make it work essentially. If that doesn't answer your question, then please resubmit.
Okay, thanks, Nigel. That's all the questions we have listed at the moment. So if there are no more questions appearing, we'll say thank you very much for listening and for your time. I hope you've all found it very informative, and I'm sure we'll do a similar presentation with some new topics again very soon. Okay, thank you, everybody.